Tonight, I'm going to tell you about something that shouldn't exist. Something so impossibly large that when astronomers first measured it, they thought their instruments were broken. They checked again, and again. The numbers kept coming back the same. What they had found was a structure so vast that light, traveling at 186,000 miles per second, needs 10 billion years just to cross from one side to the other. That's longer than the Earth has existed. Longer than our sun has been burning. This thing is so enormous that according to our best understanding of physics, it simply cannot be real. The universe hasn't existed long enough for something this big to form. And yet, there it is, stretching across the distant cosmos, waiting to be explained. Before we dive in, if you enjoy these kinds of deep explorations into the universe's strangest mysteries, a quick like or subscribe would really help this channel grow. It's a small gesture, but it means a lot to me. Now, let's begin. Let's start somewhere familiar. Let's start with home. Right now, you're sitting on a planet. A ball of rock and metal about 7,900 miles across, spinning through space at roughly 67,000 miles per hour as it orbits an average star in an unremarkable region of a galaxy that contains hundreds of billions of other stars. Earth feels big to us, and it should. From our perspective, standing on its surface, it seems enormous. The horizon stretches away in every direction. Mountains rise miles into the sky. Oceans span thousands of miles. You could spend your entire life traveling and never see every corner of it. The continents alone would take years to explore properly. The Amazon rainforest, the Sahara Desert, the frozen expanses of Antarctica, the crowded cities of Asia. Each region could consume a lifetime of exploration, and you'd still only scratch the surface. If you wanted to walk around Earth's equator, covering about 25,000 miles, walking 8 hours a day at a steady pace of 3 miles per hour, it would take you roughly 3 years. 3 years of continuous walking just to circle the planet once. That's a long journey. That's longer than most people spend in high school. You'd walk through jungles, deserts, mountains, and coastlines. You'd cross rivers and valleys. You'd experience every climate Earth has to offer. And after all that, after 3 years of non-stop travel, you'd arrive right back where you started. Earth is genuinely large from a human perspective. The surface area of our planet is about 197 million square miles. If you wanted to visit every square mile and spent just 1 second in each location, it would take you over 6 years of continuous travel. The United States, one of the largest countries, covers only about 3.8 million square miles. That's less than 2% of Earth's total surface. You could fit the entire United States inside Earth's surface area more than 50 times. For most of human history, Earth was everything. It was the entire universe as far as anyone knew. Ancient civilizations believed the sky was a dome overhead, with lights fixed to it. The ground beneath was flat and extended forever in all directions. This made sense based on what people could see. When you stand on the surface and look out at the horizon, the Earth does appear flat. The curvature is too subtle to notice without getting very high up. But here's where things start to shift. Because as soon as you look up, as soon as you start comparing Earth to other things in space, it begins to shrink. Not physically, of course, but in terms of how we think about it. Earth stops being everything and becomes just one thing among many. And as we keep zooming out, it gets smaller and smaller until it becomes something almost impossible to see. Our nearest cosmic neighbor is the Moon. It orbits Earth at an average distance of about 230 39,000 miles. That's roughly the distance you'd travel if you drove around Earth's equator 9.5 times. It seems far, and it is far by human standards. When the Apollo astronauts traveled to the moon, it took them about 3 days to get there, traveling at speeds of around 25,000 miles per hour. 3 days to reach something you can see with your naked eye every night. Something that appears as big as your thumbnail held at arm's length. The moon itself is about 2,160 miles across. That's roughly 27% of Earth's diameter. If Earth were a basketball, the moon would be about the size of a tennis ball. Smaller than Earth, but not dramatically so. You could fit about 50 moons inside Earth's volume, which sounds like a lot until you realize that later, we'll be talking about objects that could fit millions or billions of Earths inside them. But here's what most people don't realize. The distance between Earth and the moon is about 30 times Earth's diameter. Imagine placing 30 Earths in a line, edge to edge. That chain of planets would stretch from here to the moon. That's how much empty space exists between us and our closest celestial neighbor. Most illustrations of the Earth-Moon system show them much closer together than they actually are. The reality is that there's a vast amount of nothing between us and the moon. This is the first hint of something important. Space is mostly empty. Even in our immediate cosmic neighborhood, the distances are enormous compared to the sizes of the objects themselves. The moon looks close because we can see it so clearly, but 3 days of rocket travel separate us from it, and that's using some of the most powerful rockets ever built. The moon's relationship with Earth is actually quite unique in the solar system. Most moons are tiny compared to their parent planets, but our moon is relatively large. The Earth-Moon system is sometimes called a double planet because the moon is so substantial relative to Earth. The moon's size has real effects on our planet. It creates the tides we experience every day. It helps stabilize Earth's axial tilt. Without the moon, Earth's axis might wobble dramatically over time, causing extreme climate variations that could make complex life difficult or impossible. Now let's go farther. Let's visit the Sun. The Sun sits about 93 million miles from Earth. That distance has a special name in astronomy. It's called 1 astronomical unit, or AU. Light from the Sun takes about 8 minutes and 20 seconds to reach us. Think about that for a moment. If something happened on the Sun right now, if it suddenly changed color or dimmed or even exploded, we wouldn't know for over 8 minutes. The light carrying that information would still be traveling toward us through space. We'd keep seeing the Sun as it was, not as it is, for over 8 minutes. If you could somehow drive to the Sun at highway speeds, say 60 miles per hour, it would take you about 176 years to get there. Your great-great-grandchildren would arrive. The fastest spacecraft humans have built, the Parker Solar Probe, travels at speeds exceeding 400,000 miles per hour at its closest approach to the Sun. Even at that incredible speed, which is about 500 times faster than a bullet, the probe takes months to complete its orbits. The Sun itself is massive. Its diameter is about 864,000 miles. That's 109 times larger than Earth's diameter. If the Sun were hollow, you could fit about 1.3 million Earths inside it. Let that sink in for a moment. Every mountain, every ocean, every city, every person who has ever lived, all of human history happened on a planet that could fit inside the Sun more than 1 million times over. Every war fought, every empire built, every love story and tragedy, all of it played out on something that's essentially a tiny marble compared to the Sun. The Sun contains 99.86% of all the mass in our solar system. Everything else, all the planets, moons, asteroids, and comets combined, makes up only about 0.14%. The Sun is the dominant object in our neighborhood, and nothing else even comes close. Jupiter, the largest planet, contains only about 1,000th of the Sun's mass. Earth contains only about 1/300,000th. The Sun's power is staggering. Every second, it converts about 600 million tons of hydrogen into helium through nuclear fusion. This process releases an enormous amount of energy. The Sun produces more energy in 1 second than all of human civilization has produced in its entire history. The temperature at the Sun's core reaches about 27 million degrees Fahrenheit. The pressure is about 260 billion times Earth's atmospheric pressure. But here's the thing. The Sun is actually a pretty ordinary star. Astronomers classify it as a G-type main sequence star, sometimes called a yellow dwarf. It's about 4.6 billion years old, roughly middle-aged. It has enough fuel to keep burning for another 5 billion years or so before it begins to die. In the grand catalogue of stars, the Sun is unremarkable. It's not particularly large, not particularly bright, not particularly hot or cool. It's just average, and yet, from Earth's perspective, it dominates everything. It provides all the light and heat that makes life possible on our planet. It governs the orbits of all the planets. It's been worshipped as a god by countless human civilizations. The ancient Egyptians called it Ra. The Greeks called it Helios. The Aztecs built pyramids to honor it. The Sun seems central and important, but it's just one star among many. One ordinary star in a galaxy containing hundreds of billions of others. Let's expand our view to include the other planets. Our solar system extends far beyond Earth and the Sun. Mercury huddles closest to the Sun, baked and frozen in its extreme orbit. It has almost no atmosphere, which means there's nothing to protect it from meteorite impacts, or to trap heat. Mercury's surface endures temperature swings exceeding 1,000 degrees, from 800 degrees Fahrenheit under direct sunlight to negative 290 degrees in darkness. Mercury takes only 88 Earth days to orbit the Sun, but it rotates very slowly. One day on Mercury, from sunrise to sunrise, lasts 176 Earth days. Imagine living on a world where a single day lasts longer than a year. Venus follows, shrouded in its toxic atmosphere. Venus is sometimes called Earth's twin because of its similar size, but the similarities end there. The atmosphere is thick with carbon dioxide, creating a runaway greenhouse effect. The surface temperature averages about 900 degrees Fahrenheit, hot enough to melt lead. Venus is actually hotter than Mercury, even though it's farther from the Sun. The pressure at Venus's surface is about 90 times higher than Earth's, equivalent to being 3,000 feet underwater in Earth's oceans. Venus also rotates backward compared to most planets, and so slowly that one Venusian day lasts longer than one Venusian year. Then Earth, our blue marble at the perfect distance for liquid water. Mars rounds out the inner rocky planets, a cold desert that once knew flowing rivers. Mars is smaller than Earth, with a diameter of about 4,212 miles. That's about 53% of Earth's diameter. Mars has polar ice caps made of water ice and frozen carbon dioxide. It has the largest volcano in the solar system, Olympus Mons, which rises about 72,000 feet above the surrounding terrain. That's nearly 3 times the height of Mount Everest. Mars once had liquid water on its surface. Ancient riverbeds and lake beds are visible from orbit. But something happened. Mars lost most of its atmosphere. The planet is smaller than Earth, so its gravity is weaker. But the main reason is that Mars lost its magnetic field. Without this protection, the solar wind slowly stripped away Mars's atmosphere over hundreds of millions of years. Today, Mars is a frozen desert with an atmosphere so thin that liquid water cannot exist on the surface. Beyond Mars lies the asteroid belt, a vast region populated by thousands of rocky fragments. These are the building blocks that never quite became a planet. Jupiter's gravity disrupted their formation billions of years ago, leaving them scattered in an orbital ring between Mars and the outer giants. Despite containing millions of objects, the asteroid belt is mostly empty space. If you flew through it, you'd likely never see an asteroid with the naked eye. The distances between them are enormous. Then we reach the realm of the giant planets. Jupiter dominates the outer solar system with a diameter of about 86,881 miles. That's 11 times wider than Earth. Jupiter's volume is so immense that 1,321 Earths would barely fill it. This single planet contains more mass than all the other planets combined. If Jupiter were a hollow sphere, you could fit every other planet in the solar system inside it with room to spare. Jupiter's most famous feature is the Great Red Spot, a storm larger than Earth that's been raging for at least 400 years. Wind speeds at the edges of the storm reach about 400 miles per hour. Jupiter has at least 95 known moons. The four largest, called the Galilean moons after Galileo, who discovered them in 1610, are worlds in their own right. Europa, in particular, hides something remarkable beneath its smooth, icy surface, a discovery we'll explore in a moment. Saturn follows, nearly as impressive, with its magnificent ring system. Saturn's southern diameter is about 72,367 miles, and it could contain 764 Earths within its bulk. The rings are made of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders. The rings extend tens of thousands of miles from the planet's surface, yet they're remarkably thin, as little as 30 feet thick in some places. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a piece of paper. The ice giants Uranus and Neptune dwell in the cold darkness beyond. Both are smaller than Jupiter and Saturn, but still dwarf Earth. Uranus could hold about 63 Earths. Neptune could hold about 57. Uranus is unusual because it's tilted on its side, with its axis of rotation nearly parallel to its orbital plane. No one knows exactly why. The most likely explanation is that early in the solar system's history, the planet was hit by a large object that knocked it over. But the giant planets aren't just impressive for their size, they're surrounded by moons that are worlds in their own right, places so strange and fascinating that they have become primary targets in our search for life beyond Earth. Jupiter's moon. Europa is covered in a shell of ice, smooth and cracked like a frozen eggshell. But beneath that ice, kept liquid by the gravitational flexing that Jupiter's immense gravity causes, is a global ocean. This ocean contains about twice as much water as all of Earth's oceans combined, hidden beneath miles of ice in the cold darkness of the outer solar system. Where there's liquid water, there might be life. Europa is one of the most promising places in our solar system to search for organisms beyond Earth. Saturn's moon Titan is even stranger. It's the only moon in the solar system with a thick atmosphere, denser than Earth's atmosphere in fact. The surface pressure on Titan is about 50% higher than on Earth, but Titan is so cold, about negative 290 degrees Fahrenheit. That water ice is as hard as rock. Instead of water, Titan has lakes and seas of liquid methane and ethane. Rain falls from hydrocarbon clouds. Rivers carve channels through the frozen landscape. It's a world with a complete liquid cycle, just like Earth, but with chemistry so alien that we can barely imagine what might live there. Then there's Enceladus, a small moon of Saturn only about 313 miles across. Despite its tiny size, Enceladus is geologically active. Geysers at its south pole shoot plumes of water ice hundreds of miles into space. The Cassini spacecraft flew through these plumes and detected organic molecules, the building blocks of life. Beneath the icy surface, Enceladus harbors a liquid water ocean heated by tidal forces. This tiny frozen moon has become one of the most intriguing places in the solar system. These moons remind us that the solar system is far more complex and interesting than just a collection of planets orbiting the sun. Even in our own cosmic backyard, there are mysteries waiting to be explored, worlds that might harbor life in forms we've never imagined. Neptune, the most distant planet, orbits the sun at an average distance of about 2.8 billion miles. That's 30 times farther from the sun than Earth is. Light from the sun takes about 4 hours to reach Neptune. At this distance, the sun would appear as just a very bright star in the Neptunian sky, not the overwhelming source of light and heat we experience on Earth. Beyond Neptune lies the Kuiper Belt, a region of icy bodies left over from the solar system's formation. Pluto resides here, along with thousands of other frozen worlds. Pluto is only about 1,473 miles across, about 18% of Earth's diameter. The Kuiper Belt extends from Neptune's orbit outward for billions of miles, containing countless frozen objects that have remained largely unchanged since the solar system formed 4.5 billion years ago. But even the Kuiper Belt isn't the true edge of our solar system. Far beyond, almost incomprehensibly distant, lies the Oort cloud. This vast spherical shell of icy objects surrounds our solar system like a cosmic bubble. It begins at about 2,000 times Earth's distance from the Sun and extends outward to nearly 2 light years. That's almost halfway to the nearest star. Objects in the Oort cloud are so far away that they're barely affected by the Sun's gravity. They're more like prisoners loosely held than objects firmly in orbit. No human eye has ever seen an Oort cloud object directly. We know it exists only because comets occasionally fall inward from this distant realm, their icy surfaces vaporizing as they approach the sun's warmth. The solar system is vast. It extends for trillions of miles. And yet, in all that space, Earth is one small rocky planet, 8,000 miles across, orbiting, relatively close to the sun. If we made a scale model where the sun was the size of a basketball, Earth would be smaller than a peppercorn, positioned about 26 feet away. Neptune would be about half a mile distant. You'd need a football field just to show the orbit of Neptune at this scale. And the nearest star? It would be more than 4,000 miles away. This brings us to our next step outward. The stars. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system. It's about 4.24 light years away. A light year is the distance light travels in 1 year, which is about 5.88 trillion miles. So Proxima Centauri is roughly 25 trillion miles away. Let me put that in perspective. Remember how the Sun is 93 million miles from Earth? Proxima Centauri is about 268,000 times farther away than that. If the distance from Earth to the Sun was 1 inch, the distance to Proxima Centauri would be about 4 miles. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object from Earth. It's been traveling for nearly 50 years, moving at about 38,000 miles per hour. That's incredibly fast by human standards. At that speed, you could travel from New York to Los Angeles in about 4 minutes. You could circle the Earth in about 40 minutes. And yet, at that speed, Voyager 1 would need about 73,000 years to reach Proxima Centauri. 73,000 years. Human civilization is only about 10,000 years old. Voyager would need to travel for 7 times longer than all of recorded human history just to reach the nearest star. And it's not even aimed in that direction. This is the reality of interstellar distances. The gaps between stars are so immense that crossing them remains far beyond our current technological capabilities. With our fastest spacecraft, it would take tens of thousands of years to reach even the nearest star. The distances are simply staggering. Proxima Centauri itself is a small red dwarf star. It's only about 14% of the Sun's diameter and contains only about 12% of the Sun's mass. It's so dim that you can't see it with the naked eye, even though it's the closest star to us. Red dwarfs like Proxima Centauri are the most common type of star in the galaxy, making up about 70% of all stars. But they're all so faint that none of them are visible without a telescope. The stars you can see when you look up at the night sky are mostly larger and brighter than the Sun. Some are giants and supergiants, stars that have exhausted the hydrogen in their cores and expanded to enormous sizes. Betelgeuse, the red supergiant in the constellation Orion, has a diameter of about 600 million miles. That's roughly 700 times larger than the Sun. If you placed Betelgeuse where the Sun is, it would extend past the orbit of Mars. Earth would be deep inside the star, vaporized instantly. But even Betelgeuse isn't the largest. UY Scuti, one of the largest known stars, has a diameter of about 1.7 billion miles. That's roughly 1,900 times larger than the Sun. If UY Scuti replaced the Sun, it would extend past the orbit of Saturn. The volume of UY Scuti is so staggering that approximately 6.5 trillion Earth-sized spheres could occupy the same space. These giant stars are impressive, but they're also rare. Most stars are smaller and dimmer than the Sun. The universe is populated mostly by faint red dwarfs, not spectacular giants. Within about 20 light-years of Earth, there are about 130 known star systems. Some are single stars like our Sun. Others are binary systems with 2 stars orbiting each other, or even triple star systems like Alpha Centauri. This is our stellar neighborhood. A small collection of stars, separated by light years of empty space. And every star you can see with your naked eye, every single one, belongs to a single structure. A structure that contains hundreds of billions of other stars, most too distant or too faint to see without powerful telescopes. That structure is called the Milky Way. When you look up at the night sky on a clear, dark night, away from city lights, you can see a faint band of light stretching across the darkness. That band is the Milky Way. The combined glow of billions of distant stars, all part of our galaxy. The ancient Greeks called it the Milky Way because it looked like spilled milk across the sky. They had no idea what it really was. It took until the 20th century for astronomers to understand that this band of light was actually our galaxy seen from the inside, and that the universe contained many other galaxies just as large or larger. The Milky Way has been our home for as long as humans have existed. Every story told under the stars, every myth about the heavens, every prayer directed upward, all of it happened within this one structure. For most of human history, people thought the Milky Way was the entire universe. Everything that existed was contained within that faint band of light. They were wrong by a factor of trillions, but before we leave the realm of individual stars, I want you to hold on to something. Remember how vast these distances seem. Remember how a single light year, the distance light travels in 1 year, is almost beyond comprehension. Remember how the nearest star would take tens of thousands of years to reach with our fastest spacecraft. Because as we zoom out further, as we start looking at larger and larger structures, even light years will start to seem small. The numbers we're about to encounter will make the distances to nearby stars look like nothing at all. The Milky Way awaits. And beyond it, structures so large they strain the limits of human imagination. The Milky Way is a spiral galaxy. If you could somehow travel millions of light years away and look back at it, you'd see a vast rotating disk of stars, gas, dust, and dark matter, all held together by gravity. It would look like a giant pinwheel, with graceful spiral arms extending from a bright central bulge, spinning slowly through the darkness of space. But we can't see it from the outside. We're trapped inside, like fish trying to understand the shape of their aquarium while swimming through the middle of it. Everything we know about the Milky Way's structure comes from careful observations and clever deductions, piecing together a picture of our home from the inside out. We've mapped the positions of stars. We've traced the spiral arms using young, hot stars and clouds of glowing gas. We've measured the motions of stars to understand how the galaxy rotates. And from all this data, we've built up a picture of our cosmic home. The Milky Way stretches about 100,000 light years from one side to the other. Let me help you understand what that distance actually means. Light travels at about 186,000 miles per second. In 1 year, light covers about 5.88 trillion miles. That's a light year. And our galaxy is 100,000 of those lined up end to end. If you could somehow travel at the speed of light, which you can't because nothing with mass can reach that speed, it would take you 100,000 years to cross our galaxy. 100,000 years. Modern humans, Homo sapiens, have only existed for about 300,000 years. You could have started your journey when the first anatomically modern humans were walking the African savanna, traveled continuously at the speed of light without ever stopping, and you'd only be about 1/3 of the way across the galaxy today. The last time something could have crossed the Milky Way, starting 100,000 years ago, Neanderthals still walked the Earth alongside our ancestors. Humans hadn't yet migrated to Australia or the Americas. We hadn't invented agriculture, hadn't built cities, hadn't developed writing. We were still living as hunter-gatherers in small tribal groups. And in all that time, light would have just barely made it from one side of the galaxy to the other. Inside this structure, there are somewhere between 100 billion and 400 billion stars. The exact number is hard to pin down because counting stars from inside the galaxy is like trying to count all the trees in a forest while standing in the middle of it. Dust blocks our view in many directions. dim stars are hard to detect, and the galaxy is so large that we can't see all of it at once. Different methods of counting give different results, which is why the estimates vary so widely. Let's try to make sense of those numbers. If there are 200 billion stars in the Milky Way, a conservative middle estimate, and you try to count them at a rate of 1 per second, it would take you over 6,300 years to finish. You'd need to have started counting during the Bronze Age, before the pyramids of Egypt were built, and you'd still be counting today. That's how many stars are in our galaxy. Our sun is just one of these stars, one among hundreds of billions. It sits about 26,000 light years from the galactic center, tucked into a minor spiral arm called the Orion Spur. We're not at the center of anything special. We're not in a prominent spiral arm. We're in the suburbs of the galaxy, in a relatively quiet neighborhood between two larger spiral arms called the Sagittarius Arm and the Perseus Arm. The Sun orbits the galactic center at a speed of about 230 kilometers per second. That's about 143 miles per second. At that speed, you could travel from New York to Los Angeles in about 17 seconds. You could circle the Earth in about 3 minutes. That's incredibly fast by any human standard. But even at this incredible speed, it takes the Sun about 225 million years to complete one orbit around the galaxy. This orbital period is sometimes called a galactic year, or a cosmic year. Think about what that means. The last time the Sun was at its current position in its orbit around the galaxy, dinosaurs were just beginning to evolve on Earth. The first dinosaurs appeared about 230 million years ago. So, roughly 1 galactic year ago, dinosaurs were brand new, just starting their 165 million year reign over the planet. The time before that, about 450 million years ago, life had only recently emerged from the oceans onto land. The first plants and insects were just beginning to colonize the continents. Fish were the most advanced animals on Earth. Earth has completed only about 20 orbits around the galaxy since it formed 4.5 billion years ago. 20 trips around. That's it. The galaxy is so large that even traveling at 230 kilometers per second, our solar system has only gone around 20 times in its entire existence. At the very center of the Milky Way sits something remarkable. A supermassive black hole called Sagittarius, a star. This black hole has a mass of about 4 million times the mass of our Sun, all compressed into a region smaller than our solar system. If you could somehow see it, the event horizon, the boundary beyond which nothing can escape, would be about 17 times the diameter of the Sun. That sounds large, but remember we're talking about 4 million solar masses crammed into that space. Sagittarius, a star, is the gravitational anchor around which our entire galaxy rotates. Every star in the Milky Way, including our Sun, orbits around this central black hole. It's the heart of our galaxy, even though it's invisible to ordinary telescopes because nothing escapes from a black hole, not even light. We know Sagittarius is stars there because we can see its effects. We can watch stars near the galactic center orbiting around something invisible. One star, called S2, orbits the black hole once every 16 years, at speeds reaching several percent of the speed of light. That's tens of millions of miles per hour. At its closest approach, S2 comes within about 11 billion miles of the black hole, roughly the distance from the Sun to Saturn. The region around Sagittarius A star is chaotic. Stars are packed much more densely than in our neighborhood. Gravitational forces are intense, radiation levels are high. The center of the galaxy is a violent, dangerous place that would be lethal to any life as we know it. If Earth were located near the galactic center, we would be bombarded by radiation from nearby stars, disrupted by gravitational perturbations from passing stars, and subjected to periodic bursts of energy when gas falls into the central black hole. But 26,000 light years away, where the sun resides, things are much calmer. The stars are more spread out. Supernovae are less common. The radiation is less intense. Our position in the galactic suburbs might have been essential for life to develop on Earth. We're far enough from the chaotic center to be safe, but not so far out that heavy elements needed for rocky planets and complex chemistry are scarce. The Milky Way has several distinct regions. The central bulge is a dense, roughly spherical collection of old stars. This region is about 10,000 light years across and contains billions of stars packed much more closely than in our neighborhood. If you lived on a planet near the galactic center, your night sky would be filled with thousands of bright stars, making the night almost as bright as twilight on Earth. Surrounding the bulge is the disk, a flattened structure about 1,000 light years thick, where most of the galaxy's gas, dust, and star formation occurs. The spiral arms are denser regions. Within this disk where gas is compressed and new stars are born. The arms appear bright because they contain lots of young, hot, blue stars. These massive stars live fast and die young, rarely lasting more than a few million years. By the time they die, they've barely moved from where they were born, so they stay in the spiral arms. The Sun, being an older, more stable star, at about 4.5 billion years old, has had time to drift away from whatever spiral arm it was born in. We're now between spiral arms in a relatively calm region. This might actually be beneficial for life. Spiral arms are more dangerous places, with more supernovae and more intense radiation. Surrounding the disk is the galactic halo, a roughly spherical region containing old stars and globular clusters. The halo extends about 130,000 light years from the galactic center. The stars in the halo are among the oldest in the galaxy, formed when the Milky Way was just beginning to take shape over 13 billion years ago. The halo also contains dark matter. We can't see dark matter directly, but we can detect its gravitational effects. The Milky Way's dark matter halo extends even farther than the visible halo, possibly out to 600,000 light years or more. Most of the Milky Way's mass is actually dark matter, not stars and gas. When we talk about the galaxy's total mass, which is about 1.5 trillion times the mass of the Sun, most of that is invisible dark matter that we can only detect through its gravitational influence. The Milky Way is genuinely large. It's one of the bigger galaxies in the observable universe. About 95% of all galaxies are smaller than the Milky Way. This might surprise you if you've heard about giant galaxies out there, but the truth is that most galaxies are dwarf galaxies, containing only a few million or a few billion stars. They're typically just a few thousand light years across, and they're everywhere. For every large galaxy like the Milky Way, there are dozens or hundreds of smaller galaxies scattered around. The Milky Way, with its hundreds of billions of stars and 100,000 light-year diameter, is exceptional. If galaxies were people, the Milky Way would be in the top 5% by size. That's genuinely impressive. But here's where things start to shift again. Because the Milky Way isn't alone. It has neighbors, lots of them. And when you zoom out far enough, even a large galaxy like ours becomes just one piece in something much larger. The closest large galaxy to us is Andromeda, also called M31. It sits about 2.5 million light years away. That distance is so vast that the light you see when you look at Andromeda tonight left that galaxy 2.5 million years ago. When those photons began their journey toward Earth, our ancestors hadn't yet evolved into modern humans. Homo erectus was walking the African plains. The genus Homo had only recently appeared. Our ancestors were just beginning to use simple stone tools. Every photograph of Andromeda shows the galaxy as it was millions of years ago, not as it is now. We have no way of knowing what Andromeda looks like right now, at this very moment. That information is still traveling toward us across the void, and it won't arrive for another 2.5 million years. Andromeda is actually larger than the Milky Way. It contains about 1 trillion stars, more than twice what our galaxy has. Its diameter is about 220,000 light years, more than double the Milky Way's span. If you could somehow see both galaxies from above, Andromeda would clearly be the bigger sibling. In our cosmic neighborhood, we're actually the second biggest galaxy, not the first. On a clear, dark night, you can see Andromeda with your naked eye. It appears as a faint, fuzzy smudge in the constellation Andromeda. What you're seeing is the combined light of 1 trillion stars, blurred together by distance into a single pale glow. It's the most distant object you can see without a telescope, and it's been observed by humans for thousands of years, though ancient people had no idea what they were looking at. Andromeda is also moving toward us. The two galaxies are approaching each other at about 70 miles per second, roughly 250,000 miles per hour. In about 4.5 billion years, Andromeda and the Milky Way will collide. The two great spirals will pass through each other, their gravity disrupting both structures, pulling out long streamers of stars. They'll swing around, fall back together, pass through each other again. This dance will repeat several times over about 1 billion years, until finally the two galaxies merge into a single, large elliptical galaxy. Don't worry about the collision. Even when galaxies merge, the distances between individual stars are so vast that actual collisions between stars are incredibly rare. Stars are like fireflies in a vast, dark warehouse. When two swarms of fireflies pass through each other, the individual fireflies almost never touch. The same is true for stars in merging galaxies. Our solar system will likely survive the merger intact, though it might end up in a very different location in the new combined galaxy. By the time this merger happens, about 4.5 billion years from now, the Sun will be nearing the end of its life anyway. It will have exhausted most of its hydrogen fuel and begun expanding into a red giant. Earth will likely be uninhabitable regardless of what happens to the galaxy. So while the Andromeda collision sounds dramatic, it's not something to lose sleep over. What many people don't realize is that the Milky Way has already consumed other galaxies. Our galaxy isn't pristine. It's a cannibal, and the evidence of its past meals is written in the motions and compositions of its stars. Right now, at this very moment, the Milky Way is in the process of devouring a smaller galaxy called the Sagittarius Dwarf Elliptical Galaxy. This small galaxy wandered too close to the Milky Way and got caught in its gravitational grip. Over the past 1 billion years or so, the Milky Way has been slowly tearing it apart, stripping away its stars and absorbing them into our own galaxy. The Sagittarius Dwarf has already looped around the Milky Way several times, leaving streams of stars scattered across the sky like breadcrumbs marking its path. Astronomers have identified the remnants of other ancient galaxies that the Milky Way consumed long ago. By studying the chemical compositions and motions of stars, they can identify groups that don't quite fit with the rest of the galaxy. These are the fossils of galaxies that were absorbed billions of years ago. One such ghost, called Gaia Enceladus, or the Gaia Sausage, collided with the Milky Way about 10 billion years ago. It was a significant merger, perhaps the most important in our galaxy's history, and it helped shape the Milky Way into the structure we see today. This process of galactic cannibalism is common throughout the universe. Large galaxies grow by consuming smaller ones. The Milky Way has eaten many smaller galaxies in its past, and will eat more in its future before eventually merging with Andromeda. Every large galaxy has a similar history. A story of growth through consumption written in the scattered remnants of devoured neighbors. The Milky Way and Andromeda are the two largest members of a collection called the Local Group. This is our cosmic neighborhood, a gravitationally bound collection of about 50 galaxies, spanning roughly 10 million light-years. Most of the galaxies in the Local Group are small dwarf galaxies. The Large Magellanic Cloud contains about 10 billion stars and is about 14,000 light-years across. The Small Magellanic Cloud is even smaller. Both are visible from the southern hemisphere as fuzzy patches in the night sky, and both are currently being slowly torn apart by the Milky Way's gravity. Over the next few billion years, they'll be completely absorbed, their stars becoming part of our galaxy. Then there's Triangulum, also called M33, the third largest galaxy in the Local Group. It contains about 40 billion stars and is about 60,000 light-years across. It's less than half the size of the Milky Way and might actually be a satellite of Andromeda rather than an independent member of the Local Group. The rest are dwarfs, dozens of small galaxies containing just millions of stars. Some, like the ultra-faint dwarf galaxies discovered in recent decades, contain only a few thousand stars. Segway 1, discovered in 2006, contains only about 1,000 stars. It's so small and faint that it's barely a galaxy at all. It's more like a large star cluster that happens to be bound by its own dark matter. The Local Group is bound together by gravity. The galaxies within it don't just drift randomly through space. They orbit around a common center of gravity located somewhere between the Milky Way and Andromeda. Over billions of years, many of these smaller galaxies will be consumed by the larger ones, their stars absorbed and scattered. The Local Group will eventually become dominated by the merged Milky Way Andromeda galaxy, which some astronomers have nicknamed Milkomeda or Milkdromeda. But here's the critical insight. The Local Group is tiny. 10 million light-years sounds enormous, and it is by human standards. But in the context of the universe, it's almost nothing. The Local Group is just one small collection of galaxies in a much, much larger structure. That larger structure is called the Virgo supercluster. A supercluster is exactly what it sounds like. It's a cluster of galaxy clusters. Instead of talking about individual galaxies, we're now talking about groups of galaxies, all gravitationally connected in an enormous structure. The Virgo supercluster contains at least 100 galaxy groups and clusters. The dominant structure is the Virgo cluster itself, located about 54 million light-years from us. This cluster contains between 1,200 and 2,000 galaxies. Many of these galaxies are much larger than anything in our Local Group. M87, the giant elliptical galaxy at the heart of the Virgo cluster, is a monster. It contains about 1 trillion stars, similar to Andromeda, but it's a completely different type of galaxy. Elliptical galaxies are roughly spherical or football-shaped, with no spiral arms and very little gas or dust. They're mostly made of old, red stars, and they've largely stopped forming new stars. M87 grew to its enormous size by consuming other galaxies over billions of years, absorbing them one by one until it became the dominant galaxy in its cluster. M87 is also famous for being the first galaxy where astronomers directly imaged a black hole. In 2019, the Event Horizon Telescope collaboration released an image showing the shadow of M87's central supermassive black hole. That black hole has a mass of about 6.5 billion times the mass of our Sun. To put that in perspective, the black hole at the center of the Milky Way, Sagittarius A star, is about 4 million solar masses. M87's black hole is more than 1,600 times more massive. It's one of the largest black holes ever measured. The Virgo supercluster as a whole spans about 110 million light-years and contains roughly 100 trillion stars. Let's put that in perspective. Remember how the Milky Way seemed big at 100,000 light-years across? The Virgo supercluster is 1,100 times wider. Our entire galaxy, with all its hundreds of billions of stars, is just a tiny speck in this larger structure. If the Virgo supercluster were the size of a city, the Milky Way would be smaller than a single house in that city. Actually, it would be more like a single room in a house in that city. Everything we've talked about so far, Earth, the solar system, the nearest stars, our entire galaxy, all of it fits into something roughly the size of a room when you scale up to the Virgo supercluster. But even the Virgo supercluster isn't the biggest thing out there. Not even close. In 2014, astronomers discovered something extraordinary. Using careful measurements of galaxy motions and distances, they mapped the flow of galaxies across a huge region of space. What they found was that the Virgo supercluster itself is just a small part of an even more massive structure. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. The name was suggested by Nawaa Napoleon, an associate professor of Hawaiian language, and it captures something of the awe astronomers felt when they realized what they'd found. Laniakea is a supercluster of superclusters. It contains about 100,000 galaxies spread across 520 million light-years. The Milky Way, the Virgo supercluster, and thousands of other structures are all part of Laniakea. All of these galaxies, including ours, are slowly moving towards the center of Laniakea, drawn by the combined gravity of all that mass. The center of Laniakea, the point toward which everything is flowing, is called the Great Attractor. This is a region of space with enormous gravitational pull, drawing thousands of galaxies toward it at speeds of several hundred kilometers per second. The Great Attractor has been a mystery for decades. Astronomers could detect its gravitational effects. They could see that galaxies in our region of space are all moving towards a particular point, but they couldn't see what was there because the Great Attractor sits behind the plane of the Milky Way from our perspective. The dust and gas in our own galaxy block our view in that direction. It's like trying to see something on the other side of a fog bank. We know it's there, but we can't see it directly. Using different types of light, radio waves, infrared, and X-rays, astronomers have pieced together a picture of what the Great Attractor region contains. It's not a single object. It's a concentration of several massive galaxy clusters, including the Norma cluster and the Centaurus cluster. If you shrunk Laniakea down so that the Milky Way was the size of a grain of sand, Laniakea itself would be about the size of a large room. We've gone from thinking our galaxy is everything to realizing it's less than a speck of dust in a structure so large it defies easy comprehension. But here's what really bends the mind. Even Laniakea isn't the end of the story. Laniakea is huge, but it's just one supercluster among many. The universe contains countless superclusters, each containing thousands or hundreds of thousands of galaxies. And when astronomers map the distribution of all these galaxies across the observable universe, a pattern emerges. Galaxies aren't randomly scattered through space like grains of sand on a beach. Instead, they cluster along filaments and walls, forming a structure that astronomers call the cosmic web. The cosmic web is the large-scale structure of the universe. It looks like a three-dimensional network of threads, with dense regions where galaxies cluster together and vast empty regions called voids, where very few galaxies exist. The filaments can stretch for hundreds of millions of light years. They contain millions of galaxies, all gravitationally connected, strung out along cosmic threads like pearls on a string. Where filaments intersect, you find the densest concentrations of galaxies, the massive galaxy clusters that serve as nodes in this cosmic network. The voids between the filaments are enormous. Some voids span hundreds of millions of light years. Inside them, there are very few galaxies. The density of matter in a void is much lower than average. If you were somehow transported to the center of a large void and looked out in any direction, the nearest galaxy clusters would be hundreds of millions of light years away. The universe would look much emptier from that vantage point. These voids make up about 80% of the universe's volume. Most of space is empty. The galaxies, clusters, superclusters, and filaments that we can see occupy only a small fraction of the total volume. The universe is like a vast foam, with galaxies concentrated in the thin walls between enormous bubbles of nothing. This structure arose from the earliest moments of the universe's existence. Shortly after the Big Bang, matter was almost perfectly uniformly distributed. But there were tiny variations, incredibly small differences in density from place to place. These fluctuations were quantum in origin, random variations at the smallest scales that got stretched to cosmic sizes during the rapid expansion of the early universe. Over billions of years, gravity amplified these differences. Regions that were slightly denser than average attracted more matter, becoming denser still. Regions that were slightly less dense lost matter to their surroundings, becoming voids. The result is the cosmic web we see today, a universe where matter has organized itself into an intricate network of filaments and walls surrounding vast, empty voids. Laniakea is one part of this web. There are many other superclusters, many other filaments, and some of these structures are far larger than Laniakea itself. The Sloan Great Wall, discovered in 2003 by astronomers analyzing data from the Sloan Digital Sky Survey, stretches about 1.37 billion light years across. It contains tens of thousands of galaxies arranged in a relatively thin sheet. If the Milky Way were the size of a grain of rice, the Sloan Great Wall would be longer than 10 football fields placed end to end. The CFA2 Great Wall, discovered even earlier in 1989, is another massive structure, about 500 million light years long. When it was discovered, It was the largest known structure in the universe, and it changed how astronomers thought about cosmic organization. These discoveries forced scientists to reconsider their assumptions. The universe wasn't just a random scattering of galaxies. It had structure, it had patterns, and those patterns existed on scales so large that they challenged our ability to comprehend them. But here's where things get strange. According to our best understanding of physics, there should be a limit to how large these structures can get. Gravity takes time to pull matter together. It doesn't work instantaneously. In a universe of finite age, there's only so much clumping that can occur. Only so much time for matter to gather into larger and larger structures. The Sloan Great Wall, at 1.37 billion light years, already pushes against this theoretical limit. Some astronomers wondered whether it was really a single, coherent structure or just a chance alignment of smaller structures that happened to line up along our line of sight. But then came a discovery that made the Sloan Great Wall look small. In 2013, astronomers found something that shouldn't exist. A structure so vast that it violates our understanding of how the universe evolves. A structure so large that light itself needs billions of years to cross it. They called it the Hercules-Corona Borealis Great Wall. And that's where we're going next. Before we can fully appreciate the Hercules-Corona Borealis Great Wall, we need to understand more about how astronomers discover these enormous structures and why they matter. Because finding something 10 billion light years across isn't like finding a mountain or even a continent. You can't just look at it. You can't photograph it in a single image. You have to piece it together from millions of individual observations, each one revealing a tiny fragment of a much larger picture. When you look up at the night sky, you see points of light. Some are stars in our galaxy, a few are planets in our solar system reflecting sunlight. On a very dark night, far from city lights, you might see the faint smudge of Andromeda, the nearest large galaxy. You might see the Magellanic Clouds if you were in the southern hemisphere. But that's about it. The naked eye can only see so much. Everything else, the billions of galaxies scattered across the universe, remains invisible without technology. Telescopes changed everything. When Galileo first pointed a telescope at the night sky in 1609, he saw things no human had ever seen. He saw the moons of Jupiter, the phases of Venus, the countless stars that made up the Milky Way's glow. Suddenly, the universe was larger and more complex than anyone had imagined. Over the following centuries, telescopes grew larger and more powerful. Astronomers could see fainter objects, more distant stars, and eventually, strange, fuzzy patches of light that didn't look like stars at all. These nebulae, as they were called, puzzled astronomers for generations. Some thought they might be clouds of gas within our galaxy, birthplaces of new stars. Others suspected they might be something far more extraordinary, other island universes beyond the Milky Way, each containing billions of stars of their own. The debate raged for decades. In 1920, astronomers Harlow Shapley and Heber Curtis held a famous public debate about the nature of these nebulae. Shapley argued that the Milky Way was the entire universe, and the nebulae were just gas clouds within it. Curtis argued that some nebulae were actually distant galaxies, separate from and comparable to the Milky Way. The question wasn't settled until the 1920s, when Edwin Hubble made one of the most important observations in the history of astronomy. Using the newly completed 100-inch Hooker telescope at Mount Wilson Observatory, the largest telescope in the world at the time, Hubble observed a special type of star called a Cepheid variable in the Andromeda Nebula. Cepheid variables are stars that pulse in brightness with a regular period. The key discovery made by astronomer Henrietta Leavitt in 1912 was that the period of a Cepheid's pulsation is directly related to its intrinsic brightness. If you know how bright a Cepheid actually is, and you measure how bright it appears, you can calculate how far away it must be. It's like knowing that all car headlights have the same brightness. If you see headlights that appear dim, you know the car must be far away. Hubble found Cepheids in Andromeda and calculated their distance. The result was shocking. Andromeda was about 900,000 light years away, far beyond the boundaries of the Milky Way. Later measurements revised this distance upward to about 2.5 million light years, but the conclusion was clear. The Milky Way wasn't everything. It was just one galaxy among many. The universe has suddenly become vastly, incomprehensibly larger. But how many galaxies were there? And how were they distributed through space? These questions have taken another century to answer, and we're still refining our estimates. Modern telescopes can detect galaxies billions of light years away. The light from these distant galaxies has been traveling toward us for billions of years, crossing the vast emptiness of intergalactic space at 186,000 miles per second. When we observe them, we're seeing them as they were in the distant past, when the universe was young. The most distant galaxies we can see appear as they were just a few 100 million years after the Big Bang, over 13 billion years ago. To map the large-scale structure of the universe, astronomers need to know not just where galaxies appear on the sky, but how far away they are. This is much harder than it sounds. You can't just look at a galaxy and know its distance. A bright galaxy far away might look exactly the same as a dim galaxy nearby. A giant elliptical containing 1 trillion stars at 5 billion light years might appear identical to a small dwarf galaxy containing 1 billion stars at 500 million light years. Without knowing the distance, you can't build a 3-dimensional map. Astronomers use several techniques to measure distances, each applicable at different scales. For relatively nearby galaxies within a few tens of millions of light years, they can observe Cepheid variables, the same type of star Hubble used to measure the distance to Andromeda. By comparing how bright these stars appear to how bright they actually are, astronomers can calculate the distance with reasonable accuracy. For more distant galaxies, Cepheids become too faint to observe, even with our best telescopes. Instead, astronomers use other standard candles, objects whose intrinsic brightness is known. Type E supernovae are particularly useful. These occur when a white dwarf star accumulates too much mass from a companion star and explodes in a thermonuclear detonation. Because this explosion happens at a specific mass threshold, all type Ia supernovae have roughly the same peak brightness. They're so bright that they can be seen billions of light years away, making them valuable distance markers across cosmic scales. But the most widely used method for measuring distances to very distant galaxies relies on the expansion of the universe itself. Here's where things get interesting. In 1929, Edwin Hubble made another groundbreaking discovery. By measuring the distances to nearby galaxies using Cepheids and comparing those distances to how fast the galaxies were moving, he found a striking pattern. Distant galaxies are moving away from us, and the farther away a galaxy is, the faster it's receding. This wasn't because galaxies were fleeing from us specifically. It was because the universe itself is expanding. Space is stretching, carrying galaxies with it like raisins in rising bread dough. As the dough rises, every raisin moves away from every other raisin. Raisins that are far apart move away from each other faster than raisins that are close together, simply because there's more expanding dough between them. The same is true for galaxies. The space between galaxies is expanding, and the more space there is between two galaxies, the faster they appear to move apart. This relationship between distance and recession velocity is called Hubble's law, and it's one of the most important discoveries in the history of cosmology. This expansion provides a way to measure distance. When light travels through expanding space, its wavelength gets stretched. Blue light becomes redder. This phenomenon is called redshift, and the amount of redshift tells you how much the universe has expanded since the light was emitted. The more redshifted a galaxy's light, the longer that light has been traveling, and the farther away the galaxy must be. By measuring the redshift of a galaxy's light, astronomers can determine its distance. This technique works for galaxies at any distance, even billions of light years away. It's the primary tool astronomers use to map the three-dimensional structure of the universe. The first comprehensive redshift surveys began in the 1970s and 80s. These were ambitious projects that required measuring the spectra of thousands of galaxies, one by one, to determine their redshifts and thus their distances. It was painstaking work. Each galaxy required a separate observation, and telescopes could only observe one or a few galaxies at a time. What these early surveys found was shocking. Galaxies aren't randomly distributed through space. They form patterns. They cluster along filaments and sheets. They surround vast empty regions where almost no galaxies exist. The universe has structure on scales no one had imagined. The CFA Redshift survey, conducted by astronomers at the Harvard-Smithsonian Center for Astrophysics and completed in 1989, was a landmark achievement. It mapped the positions and distances of thousands of galaxies in a slice of the sky. When the data was plotted in 3 dimensions, the result was astonishing. The survey revealed the CFA2 Great Wall, a sheet of galaxies stretching about 500 million light-years across space. This was the largest coherent structure anyone had ever found. It wasn't just a random clump of galaxies. It was an organized structure, a wall of galaxies surrounding an enormous void. The discovery suggested that the universe had organized itself into something resembling a cosmic foam or sponge. Galaxies weren't scattered randomly like stars across the sky. They were concentrated in the walls of bubbles, surrounding enormous empty regions. The universe had architecture. Later surveys found even larger structures. The 2-degree field galaxy redshift survey, completed in 2003, mapped over 200,000 galaxies. The Sloan Digital Sky Survey, which began in 2000 and continues today, has mapped the positions and distances of millions of galaxies across a significant fraction of the sky. These surveys revealed structures that dwarf the CFA2 Great Wall. The Sloan Great Wall, discovered in 2003, stretches about 1.37 billion light-years. It's more than twice the length of the CFA2 Great Wall. When it was announced, some astronomers doubted whether such a large structure could really exist. But what exactly are these structures? Why do galaxies cluster this way? To understand that, we need to go back to the very beginning. About 13.8 billion years ago, everything in the observable universe was compressed into an incredibly hot, dense state. The Big Bang wasn't an explosion in space, it was an explosion of space. Space itself expanded rapidly, and as it did, the matter and energy within it cooled and spread out. In those earliest moments, the universe was almost perfectly uniform. Matter was distributed nearly evenly throughout space. If you could have somehow surveyed the universe a few 100,000 years after the Big Bang, you would have found that the density of matter varied by only about 1 part in 100,000 from place to place. These variations were incredibly small, far smaller than you could detect with your eyes or even most instruments. But those tiny variations were enough. These primordial density fluctuations had their origins in quantum mechanics. In the very earliest moments of the universe, during a period of extremely rapid expansion called inflation, quantum fluctuations were stretched to cosmic scales. Random variations at the smallest possible scales became imprinted on the fabric of the universe itself. After inflation ended and the universe continued to expand more slowly, gravity went to work on these tiny density variations. Regions that were slightly denser than average had slightly stronger gravitational pull. They attracted matter from their surroundings, becoming denser still. Regions that were slightly less dense lost matter to denser regions, becoming emptier. This process is called gravitational collapse, and it's been happening for billions of years. Gravity is patient. It works slowly, but it works relentlessly. Over hundreds of millions of years, the tiny density variations grew larger and larger. Dense regions attracted more matter. Sparse regions became emptier. The first stars formed about 100 to 200 million years after the Big Bang, in the densest regions where enough gas had accumulated to collapse under its own gravity. These first stars were massive and short-lived, burning through their fuel in just a few million years before exploding as supernovae. But their deaths seeded the universe with heavy elements, the raw materials for future generations of stars and planets. Galaxies began to form as dark matter halos accumulated enough mass to trap gas and trigger star formation. The first galaxies were small by today's standards, containing perhaps 1 billion stars, but they merged with each other, combining into larger galaxies. The denser regions where galaxies were more common became the nodes and filaments of the cosmic web. The sparser regions, where galaxies were rare, became the voids. This process has been running for over 13 billion years. The cosmic web we see today is the result of this long, slow accumulation of matter in certain regions and its evacuation from others. The filaments and walls are where matter has concentrated. The voids are where matter has drained away. Computer simulations of the universe's evolution can reproduce this process with remarkable accuracy. Scientists programmed supercomputers with the initial conditions that existed shortly after the Big Bang, the tiny density fluctuations imprinted during inflation. Then they let gravity do its work, simulating billions of years of cosmic evolution. The results look remarkably like the real universe. Simulated galaxies cluster along filaments. They surround vast empty voids. They form walls and sheets stretching hundreds of millions of light years. The cosmic web emerges naturally from the simple action of gravity on tiny initial fluctuations. But here's the catch. These simulations also predict limits. According to our best models of how the universe evolved, there should be a maximum size to the structures that can form. Gravity doesn't work instantaneously. It propagates at the speed of light. For matter to clump together into a coherent structure, gravitational influences have to have time to propagate across the region. In a universe that's only 13.8 billion years old, there's only so much time for gravity to work. Even at the speed of light, influences can only travel so far. Gravity takes time to pull matter together. It doesn't work instantaneously. In a universe of finite age, there's only so much clumping that can occur. Only so much time for matter to gather into larger and larger structures. Anything larger simply couldn't have formed in the time available, no matter how favorable the initial conditions. The cosmological principle, one of the foundational assumptions of modern cosmology, states that on sufficiently large scales, the universe is homogeneous and isotropic. It looks the same everywhere and in every direction. The end of greatness, as this limit is sometimes called, is the scale at which this principle should become valid. Below this scale, you see structure. Above it, you should see uniformity. The Sloan Great Wall, at about 1.37 billion light years, already pushes against this limit. When it was discovered, some astronomers questioned whether it was really a single coherent structure or just a chance alignment of smaller structures. Maybe we were seeing several unrelated walls that happened to line up along our line of sight, creating the illusion of a single enormous structure. This question is harder to answer than you might think. When you're mapping the universe in 3 dimensions, you're looking out in all directions from Earth. Structures can overlap along our line of sight. What appears to be a single giant wall might actually be several smaller walls at different distances that happen to project onto the same region of the sky. Statistical tests can help distinguish between genuine structures and chance alignments, but they're not always definitive. The question of whether the Sloan Great Wall is a single structure or an illusion remains somewhat open. But then came a discovery that made the Sloan Great Wall look small. A discovery that, if confirmed, would fundamentally challenge our understanding of how the universe evolved. In 2013, a team of astronomers led by István Horváth at the National University of Public Service in Hungary, along with John Hakila at the College of Charleston and Zsolt Bagoli at Eötvös Loránd University, was studying gamma-ray bursts. These are the most energetic explosions in the known universe. Gamma-ray bursts occur when massive stars collapse at the end of their lives, forming black holes. In some cases, the collapsing star's rotation creates jets of matter and energy that punch through the star's outer layers and blast into space at nearly the speed of light. When one of these jets happens to point toward Earth, we see a gamma-ray burst, a flash of high-energy radiation that can outshine an entire galaxy for a few seconds or minutes. Gamma-ray bursts are so bright that they can be detected across billions of light years. They serve as cosmic beacons, marking the locations of distant galaxies that might otherwise be too faint to observe. By mapping the distribution of gamma-ray bursts across the sky, astronomers can trace the distribution of galaxies in the distant universe. Horváth's team was analyzing data from 2 gamma-ray observatories. The SWIFT satellite, launched in 2004, is specifically designed to detect and study gamma-ray bursts. The Fermi Gamma-Ray Space Telescope, launched in 2008, has broader capabilities but also detects many gamma-ray bursts. Together, these 2 spacecraft have detected thousands of gamma-ray bursts from across the universe. The team was looking for patterns in the distribution of gamma-ray bursts. Were they spread uniformly across the sky? Or were there regions with more or fewer bursts than expected? What they found was strange. In one particular region of the sky, in the direction of the constellations Hercules and Corona Borealis, there were far more gamma-ray bursts than expected. The excess wasn't subtle. It was statistically significant, with a probability of occurring by chance of less than 1 in 10,000. Something was concentrating gamma-ray bursts in that direction. The team then looked at the distances to these gamma-ray bursts, calculated from their redshifts. And that's when things got really strange. The excess gamma-ray bursts weren't randomly scattered across different distances. They were concentrated in a specific range between about 9 billion and 11 billion light-years away. Gamma-ray bursts closer than 9 billion light-years showed no unusual concentration. Gamma-ray bursts farther than 11 billion light-years showed no unusual concentration. But in that specific range, there was a clear, statistically significant excess. This suggested that the gamma-ray bursts were tracing a structure, a vast concentration of galaxies in that direction, at that distance. The team calculated the size of this apparent structure based on how much of the sky it covered and how far away it was. The numbers were almost impossible to believe. The structure appeared to span approximately 10 billion light-years. 10 billion light-years. Let me try to make that comprehensible, though I'm not sure it's possible. The observable universe is about 93 billion light-years across. This single structure, if it's real, spans more than 10% of that distance. If the observable universe were a large room, roughly 30 feet across, the Hercules-Corona Borealis Great Wall would stretch about 3 to 4 feet, from one wall to roughly the middle of the room. The Milky Way is 100,000 light-years across. This structure is 100,000 times larger. If the Milky Way were the size of a single grain of sand, about 1 millimeter across, the Hercules-Corona Borealis Great Wall would be about 300 feet long. That's the length of a football field. A single grain of sand versus a football field. That's the scale difference between our galaxy and this structure. Light, traveling at 186,000 miles per second, needs 10 billion years to cross from one side of the structure to the other. 10 billion years. The Earth is only about 4.5 billion years old. The Sun has only existed for about 4.6 billion years. If you had started a beam of light traveling across this structure when the Earth formed, it wouldn't even be halfway across yet. The structure is so large that it existed before the Earth did. Light from one side of the Hercules-Corona Borealis Great Wall hasn't had time to reach the other side since our solar system formed. This structure contains billions of galaxies. Each galaxy contains billions or trillions of stars. Each star potentially has planets. The total number of stars in this structure is beyond meaningful comprehension. If you tried to count them at a rate of 1 per second, you would need longer than the age of the universe to finish. But here's the problem. According to our understanding of physics, this structure shouldn't exist. The universe is 13.8 billion years old. The maximum size structure that should have been able to form through gravitational collapse in that time is about 1.2 billion light years. The Hercules-Corona Borealis Great Wall is nearly 10 times larger than that theoretical limit. It's as if you discovered a 1,000-year-old tree in a forest, where you know for certain that no tree can be older than 100 years. The math doesn't work. The physics doesn't allow it. And yet, there it is. When the discovery was announced in 2013, many astronomers were skeptical, and rightfully so. Extraordinary claims require extraordinary evidence. Maybe the analysis was wrong. Maybe there was some systematic error in the data. Maybe the gamma ray bursts weren't really tracing a structure at all. Maybe it was a statistical fluke. Even with rigorous statistical tests, random fluctuations can occasionally produce patterns that look significant but aren't real. If you look at enough data in enough ways, you'll eventually find something that appears unusual just by chance. Or maybe the structure isn't as coherent as it appears. Maybe it's actually several smaller structures, each within the theoretical limits, that happen to be aligned along our line of sight. We're seeing them overlap, creating the illusion of a single, impossible structure. These are legitimate concerns, and they haven't been fully resolved. The Hercules-Corona Borealis Great Wall remains controversial. Some astronomers accept it as real, others remain skeptical, waiting for additional evidence. But follow-up studies have largely supported the original findings. Different teams, using different methods and different data sets, have found similar concentrations of objects in the same region of the sky. The structure, whatever it is, appears to be real. And that presents a profound puzzle. If this structure exists, something is wrong with our models. The Hercules-Corona Borealis Great Wall is pointing us toward questions we don't yet know how to answer. It's a crack in our understanding, a place where our models fail to match reality. And in science, that's where the most exciting discoveries happen. The voids between cosmic filaments are almost as fascinating as the filaments themselves. When astronomers mapped the three-dimensional distribution of galaxies, they found not just concentrations but absences. Enormous regions of space where galaxies are rare or absent entirely. The largest known void is the KBC void, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who studied it extensively. This void is roughly 2 billion light-years across. Inside it, there are far fewer galaxies than in surrounding regions. It's not completely empty. There are still galaxies scattered through it, but the density is perhaps half what you'd find in an average region of space. 2 billion light-years of relative emptiness. If you were somehow transported to the center of the KBC void and looked out in any direction, the nearest major galaxy clusters would be about 1 billion light-years away. The universe would seem much emptier from that vantage point. The night sky would have far fewer galaxies visible, even with powerful telescopes. Interestingly, the Milky Way appears to be located near the edge of the KBC void. We're not in the emptiest part, but we're in a region that's less dense than the cosmic average. This might have implications for some of our cosmological measurements, though the details are still being debated. Another famous void is the Boötes void, sometimes called the Great Nothing. Discovered in 1981, it spans roughly 330 million light-years across. What makes the Boötes void particularly eerie is just how empty it is. In a region of space that size, you would expect to find roughly 2,000 galaxies based on the average density of the universe. Instead, astronomers have found only about 60. It's not just underdense, it's almost completely barren. If you lived on a planet somewhere in the middle of the Boötes void, your view of the universe would be profoundly lonely. You might look out and see almost nothing but darkness in every direction. The nearest galaxies would be over 100 million light-years away. For most of human history, if our civilization had developed there, we might have concluded that our galaxy was the only one in existence. The concept of other galaxies would have seemed absurd. The universe would have appeared as a single island of stars floating in an infinite, empty void. The Boorter's void is a reminder that the universe is not uniformly filled with galaxies. Some regions are rich with matter, packed with clusters and superclusters. Others are almost completely empty. Vast bubbles of nothing surrounded by thin walls of galaxies. The contrast is striking and raises questions about how these enormous voids formed, and why they're so thoroughly evacuated of matter. These voids make up about 80% of the universe's volume. That's a startling statistic. Most of the universe is empty. The galaxies, clusters, superclusters, and filaments that we can see and study occupy only about 20% of the total volume. The universe is like a vast foam, mostly empty space with matter concentrated in thin walls and threads, and the Milky Way sits on one of those threads. A large galaxy, yes, exceptional compared to most, but still just one island of matter in an almost unfathomably large ocean of emptiness. The cosmic web extends in all directions as far as our telescopes can see. It's the largest pattern we found in the universe. Filaments stretching for hundreds of millions of light years. Voids spanning billions of light years. Walls of galaxies surrounding empty bubbles. And somewhere in that web, in the direction of Hercules and Corona Borealis, sits the largest thing that exists. A structure 10 billion light years across. A structure that, according to our best understanding of physics, shouldn't be there at all. The Hercules-Corona Borealis Great Wall isn't just big, it's impossible. And that's what makes it so fascinating. We're about to look at it more closely. We're about to confront what it means for our understanding of the universe. And we're about to sit with the profound mystery of something that exists but shouldn't. Let's be absolutely clear about what we're dealing with. Let's lay out the facts, one by one, so you understand the full magnitude of what astronomers have found. The Hercules-Corona Borealis Great Wall is approximately 10 billion light years across. It's located between 9 and 11 billion light years from Earth, in the direction of the constellations Hercules and Corona Borealis. It was discovered in 2013 by mapping gamma-ray bursts, which trace the locations of galaxies in the distant universe. Multiple follow-up studies have confirmed that something unusual exists in that region of space, a concentration of matter on a scale that defies easy explanation. This structure is so large that it challenges the cosmological principle, the assumption we discussed earlier that the universe should appear uniform on the larger scales. There shouldn't be giant features dominating the landscape. There should just be a smooth distribution of matter, with small random variations but no enormous patterns. The existence of a structure 10 billion light years across suggests that either our understanding of cosmic structure formation is fundamentally wrong, or there's something very unusual about this region of the universe, or our observations are somehow misleading us. None of these possibilities is comfortable. All of them challenge what we thought we knew. Let me try to put this size in perspective, because the numbers are so large that they become meaningless without context. Our brains didn't evolve to comprehend distances like this. We evolved to understand the distance to the next watering hole, the distance we could walk in a day, the distance to the horizon. We can stretch our intuition to handle miles, maybe hundreds of miles, but billions of light years? That's not something any human can truly grasp intuitively. But let's try anyway. If you could somehow travel at the speed of light, the fastest speed possible in the universe according to our understanding of physics, It would take you 10 billion years to cross the Hercules-Corona Borealis Great Wall. 10 billion years. Let that duration sink in for a moment. The Earth is about 4.5 billion years old. The Sun has been shining for about 4.6 billion years. If you started crossing this structure when the Earth formed, when the first rocks were solidifying on our planet's surface, when the oceans were just beginning to condense from the steam-filled atmosphere, you wouldn't even be halfway across it yet. You'd have billions of years still to go. During a 10 billion year journey, the Sun could be born, live its entire 10 billion year lifespan, and die. It could swell into a red giant, shed its outer layers, and fade into a white dwarf. And during that same journey, another star like the Sun could form from the debris, live its entire life, and die as well. 2 complete stellar lifetimes could pass while you cross this single structure. Multiple generations of stars could form and explode as supernovae. Galaxies could collide and merge. Solar systems could form, develop planets, perhaps even evolve life, and then be destroyed when their stars died. Entire civilizations could rise, flourish for millions of years, and fall, their existence forgotten. Their monuments crumbled to dust, while light was still crossing from one side of this structure to the other. The Milky Way, our home galaxy, is 100,000 light-years across. It's one of the larger galaxies in the observable universe, bigger than about 95% of all galaxies. And yet, the Hercules-Corona Borealis Great Wall is 100,000 times larger than the Milky Way. 100,000 times. Let me give you an analogy that might help. If the Milky Way were the size of a penny, about 3/4 of an inch across, the Hercules-Corona Borealis Great Wall would be about the size of a small city. Not a building, not a neighborhood, a city. Everything we've talked about, our solar system, our galaxy, everything you can see in the night sky would fit on that penny. And this structure would sprawl across miles. Remember how we compared the Milky Way to a grain of sand and this structure to a football field? Now, imagine standing on that football field, holding that single grain of sand in your palm. That's us. That's everything we've ever known. And the field stretching away in every direction is just one structure in the distant universe. The local group, our cosmic neighborhood containing the Milky Way, Andromeda, and about 50 other galaxies, spans roughly 10 million light-years. The Hercules-Corona Borealis Great Wall is 1,000 times larger than our entire cosmic neighborhood. Everything we consider local, every galaxy close enough that we might someday imagine visiting, all of it would be a tiny speck compared to this structure. Laniakea, the supercluster of superclusters that contains the Milky Way and about 100,000 other galaxies, spans approximately 520 million light-years. It's one of the largest coherent structures we know of in our region of space. And yet, the Hercules-Corona Borealis Great Wall is nearly 20 times larger than Laniakea. 20 Laniakeas could fit across it, end to end. Remember the size of the observable universe we discussed, roughly 93 billion light-years across. The Hercules-Corona Borealis Great Wall, at 10 billion light-years, spans more than 10% of everything we can see. A single structure taking up that much of the observable universe is extraordinary. This structure contains billions of galaxies. We don't have an exact count because the structure is so distant and so vast that cataloging every galaxy within it is beyond our current capabilities. But based on the density of matter and the volume of space it occupies, the number must be in the billions. Each of those galaxies contains anywhere from millions to trillions of stars. Each of those stars potentially has planets orbiting it. If you tried to count every star in this structure at a rate of 1 per second, never sleeping, never pausing, counting continuously, it would take you longer than the current age of the universe to finish. You could have started counting at the moment of the Big Bang 13.8 billion years ago, and you'd still be counting today, with no end in sight. The total mass of this structure is almost beyond calculation. We don't have precise measurements because the structure is so far away and so enormous that direct measurements are extremely difficult. But based on the number of galaxies it contains and the typical mass of galaxies, the total mass must be staggering. It's one of the most massive concentrations of matter in the observable universe, possibly the most massive. But here's what makes this discovery truly remarkable. What sets it apart from just being big? What makes astronomers scratch their heads and question their models? It shouldn't exist. We discussed this limit earlier. About 1.2 billion light years. That's the maximum size structure that should exist according to our understanding of physics. The Hercules-Corona Borealis Great Wall is nearly 10 times larger than this theoretical limit. 10 billion light years versus 1.2 billion light years. It's not just slightly larger than expected. It's almost an order of magnitude larger. It's as if you walked into a forest where you knew with certainty that no tree could be older than 100 years, and you found a tree that was obviously 1,000 years old. The ring count doesn't lie. The tree is there. But according to everything you know about that forest, it's impossible. Think about what this means. Either our models of structure formation are fundamentally wrong, missing some crucial piece of physics that allows structures to form faster or larger than we expected. Or something very unusual happened in this region of the universe, some special circumstance that allowed this particular structure to grow beyond normal limits. Or our observations are somehow misleading us, and what appears to be a single enormous structure is actually something else entirely. None of these possibilities is comfortable. All of them require us to revise our understanding of something important. Several possible explanations have been proposed, each with its own strengths and weaknesses. One possibility is that the structure isn't as coherent as it appears. Maybe it's not a single connected structure at all. Maybe it's actually several smaller structures, each within the theoretical limits, that happen to be aligned along our line of sight. When we look in that direction, we see all of them overlapping, like mountains in the distance that appear to merge into a single ridge when you view them from far away. Each individual structure might be only a few 100 million light years across, perfectly normal, but from our vantage point, they create the illusion of a single 10 billion light year monster. This explanation has some appeal because it doesn't require changing our fundamental physics. It is consistent with everything we know about how the universe works. The coincidental alignment would be unlikely, but unlikely things do happen. With trillions of structures scattered across the universe, some alignments are statistically expected, but studies of the gamma-ray burst distribution have pushed back against this explanation. The excess gamma-ray bursts aren't spread out across a wide range of distances, which you'd expect if you were seeing multiple unrelated structures at different distances. They're concentrated in a specific range between about 9 and 11 billion light years. This suggests a single structure at a specific distance, not multiple structures strung out along the line of sight. Another possibility is that this region of the universe had unusual conditions in the very early universe. Perhaps there was a particularly large density fluctuation shortly after the Big Bang, a region that was significantly denser than average right from the start. This overdense region would have provided a seed for structure formation, attracting matter more efficiently than surrounding regions. As the universe evolved, this seed would have grown into a larger and larger structure. With a head start from the beginning, it could potentially have grown larger than structures in more typical regions of space. Maybe the Hercules-Corona Borealis Great Wall is simply the result of winning the cosmic lottery, starting with conditions that were unusually favorable for growth. But this explanation has problems too. We have very precise measurements of the density fluctuations in the early universe. The cosmic microwave background, the afterglow of the Big Bang that fills all of space, carries an imprint of those early fluctuations. The patterns in the microwave background have been mapped with extraordinary precision by satellites like COBE, WMAP, and Planck. These measurements show that the early fluctuations were remarkably uniform. They varied by only about 1 part in 100,000 from place to place. There's no obvious sign of a fluctuation large enough to seed a 10 billion light-year structure. If such an enormous initial overdensity existed, we would expect to see some hint of it in the microwave background. Some anomaly that pointed to unusual conditions in that direction. We don't see anything obvious. A third possibility is that we're seeing evidence of new physics. Maybe gravity doesn't work quite the way we think on very large scales. Maybe there are modifications to general relativity that become important when you're dealing with structures billions of light years across. Maybe there are forces or processes we don't yet understand that can organize matter on scales larger than gravity alone would allow. This is the most exciting possibility from a scientific perspective. If true, it would mean the Hercules-Corona Borealis Great Wall is pointing us toward new discoveries about how the universe works. It could be a window into physics beyond our current understanding, a clue to deeper laws that we haven't yet uncovered. Throughout the history of science, anomalies have often been the keys to new discoveries. When observations don't match predictions, it usually means we're missing something. Sometimes it's a measurement error or a misinterpretation, but sometimes it's a sign that our theories are incomplete, that there's something fundamental we haven't yet grasped. The orbit of Mercury didn't quite match Newton's predictions. For decades, astronomers tried to explain the discrepancy with conventional physics. They even proposed a hidden planet, Vulcan, orbiting close to the Sun and perturbing Mercury's orbit. But the discrepancy persisted. It was only resolved when Einstein developed general relativity, a new theory of gravity that predicted Mercury's orbit exactly. The anomaly had been pointing toward new physics all along. Could the Hercules-Corona Borealis Great Wall be a similar signpost? Could it be telling us that our understanding of gravity or cosmology is incomplete? It's possible, but we have to be careful. Invoking new physics is a serious step. The burden of proof is high. Before we overturn established theories that have passed countless tests, we need to be sure that conventional explanations really can't work. We need to rule out measurement errors, statistical flukes, and observational artifacts. The truth is, we don't know why this structure exists. A decade after its discovery, it remains one of the great puzzles in modern cosmology. Different astronomers have different opinions about how seriously to take it. Some believe it's genuinely anomalous and points toward new physics. Others suspect that further observations will reveal a more mundane explanation. The debate continues. Future telescopes and surveys may help resolve the mystery. The James Webb Space Telescope, launched in 2021, is the most powerful space telescope ever built. While it wasn't specifically designed to study large-scale structure, its ability to observe extremely distant galaxies could provide new data about the distribution of matter in the early universe. If the Hercules-Corona Borealis Great Wall is real, Webb might help us understand the environment in which it formed. Even more promising are upcoming large-scale surveys. The Vera C. Rubin Observatory, currently under construction in Chile, will systematically photograph the entire visible sky repeatedly over a 10-year period. It will catalogue billions of galaxies, providing an unprecedented three-dimensional map of the universe's structure. The European Space Agency's Euclid mission, launched in 2023, is specifically designed to map the geometry of the dark universe. These new observations will give us far more data about cosmic structure than we've ever had before. Within the next decade or two, we may have a much clearer picture of whether the Hercules-Corona Borealis Great Wall is truly a single coherent structure, or something else entirely. New data might confirm that it's exactly as anomalous as it appears, strengthening the case for new physics. Or it might reveal that we were fooled by observational artifacts or chance alignments, allowing our current models to stand. Either way, the mystery will eventually yield to careful observation and analysis. That's how science works. We ask questions, we gather data, and we let the universe tell us its secrets. What we do know is that something unusual exists in that direction, at that distance. The concentration of gamma-ray bursts is real. The statistical significance is high. Whatever is there, it's not a random fluctuation. Something is concentrating matter on an enormous scale in that region of the universe. And when you look up at the night sky, when you gaze toward the constellations Hercules and Corona Borealis, you're looking in the direction of the largest thing that exists. You can't see it, of course. It's billions of light years away, far beyond what the naked eye or even amateur telescopes can detect. The light from that structure has been traveling for 9 to 11 billion years to reach us. It left when the universe was less than half its current age, when the sun and Earth didn't yet exist, when the atoms that would eventually become your body were still scattered across distant galaxies. But it's there, stretching across 10 billion light years of space, containing billions of galaxies and countless trillions of stars, challenging our understanding of how the universe works. The discovery of the Hercules-Corona Borealis Great Wall is humbling in a way that few things are. It forces us to confront the limits of our knowledge and the vastness of our ignorance. We start this journey on Earth, a planet about 8,000 miles across. That seemed big. We compared it to the moon, to the sun, to the other planets. Earth shrank, but still seemed significant. Then we expanded to the solar system, which extends for trillions of miles, if you include the Oort cloud. The solar system seemed almost incomprehensibly large. A scale model with the sun as a basketball would put Neptune half a mile away, and the nearest star thousands of miles distant. Then, we zoomed out to the Milky Way, a galaxy containing hundreds of billions of stars. Spanning 100,000 light years, the solar system became a speck. The distances became so vast that we had to invent new units just to talk about them. Light years, thousands of light years. The numbers kept growing and our intuition struggled to keep up. Then we discovered that the Milky Way is just one galaxy among trillions. That it's part of a local group, which is part of the Virgo supercluster, which is part of Laniakea, which is part of the cosmic web. At each step, the structure we'd been contemplating shrank into insignificance compared to something larger. At each step, our sense of scale had to expand again. And now, at the end of this journey, we find something that shouldn't be possible. A structure so large that light needs 10 billion years to cross it. A structure that defies our best models of how the universe evolved. A mystery written in the arrangement of galaxies across the distant cosmos. What does this mean for us? What should we make of our place in a universe that contains something so impossibly vast? The universe doesn't care about us. It wasn't made for us. It operates according to physical laws that are entirely indifferent to human concerns. The Hercules-Corona Borealis Great Wall would exist whether or not humans ever discovered it. It stretched across the cosmos for billions of years before Earth even formed. It will still be there, slowly evolving under the influence of gravity and dark energy, long after humanity is gone. The stars don't shine for us. The galaxies don't cluster to impress us. The cosmic web wasn't woven for our benefit. The universe simply is what it is, following the laws of physics wherever they lead, creating structures and patterns that we're only beginning to understand. And yet, we did discover it. Despite being tiny, despite being confined to one small planet orbiting one average star in one medium-sized galaxy, in one unremarkable corner of one filament of the cosmic web, we figured out that this structure exists. We measured it. We mapped its location. We calculated its size. We're trying to understand why it's there. That's remarkable. That's genuinely extraordinary. That's something to feel wonder about. We're the universe looking at itself. We're matter that has organized itself into beings capable of contemplating the cosmos. We're collections of atoms that have somehow become aware of other atoms, that can trace the patterns of matter across billions of light years and ask questions about what we find. The cosmos, it turns out, is stranger and more vast than anyone imagined. But it's also comprehensible, at least partially. We've been able to figure out so much. We understand how stars work, how galaxies form, how the universe evolved from a hot, dense state to the vast web of structures we see today. Our models aren't perfect, but they're remarkably accurate. They make predictions that we can test, and those predictions usually come true. The Hercules-Corona Borealis Great Wall challenges our models. It raises questions we can't yet answer. It reminds us that the universe still holds mysteries beyond our current comprehension. But that's not a failure. That's an invitation. It's the universe telling us that there's more to learn, more to discover, more to understand. And there's something beautiful about that. There's something wonderful about living in a universe that can still surprise us. A universe where, despite all our knowledge and all our technology and all our careful observations, we can still find things that don't make sense, things that challenge our assumptions, things that force us to think harder and look deeper. The day we understand everything is the day science becomes boring. The existence of mysteries like the Hercules-Corona Borealis Great Wall means that science is still an adventure. There are still dragons on the map. There are still unexplored territories of knowledge waiting for someone to venture into them. Tonight, when you look up at the sky, remember what's out there. Remember that the stars you see are just the nearest neighbors in a galaxy containing hundreds of billions of others. Remember that those stars are just a tiny sample of what exists, that the galaxy stretches far beyond what your eyes can see. Remember that our galaxy is one of trillions, that each of those galaxies is an island of hundreds of billions of stars, separated from other islands by millions of light years of empty space. Remember that those trillions of galaxies are organized into a cosmic web of filaments and voids stretching across billions of light years. And remember that somewhere out there, in the direction of Hercules and Corona Borealis, sits the largest thing that exists. A structure so vast that it shouldn't be possible according to our current understanding of physics. A structure that contains billions of galaxies and countless trillions of stars. A mystery that's been waiting for billions of years for someone to notice it and ask why it's there. The Hercules-Corona Borealis Great Wall isn't just big. It's a puzzle. It's a question mark written across 10 billion light years of space. It's an invitation to keep exploring, keep questioning, keep looking up and wondering what else might be out there that we haven't discovered yet. We may never fully understand why it exists. We may never solve the puzzle it presents. Future astronomers might look back at our current theories and smile at how primitive they were. The way we smile at ancient astronomers who thought the stars were lights fixed to a crystalline sphere. Or they might confirm that this structure is exactly what it appears to be. A genuine anomaly that required new physics to explain. Either way, the search for understanding is valuable in itself. The questions we ask about the cosmos shape who we are as a species. Every time we look up at the night sky and wonder, we're participating in a tradition that stretches back to the first humans who noticed the stars and asked what they were. Earth is small. The solar system is larger but still finite. The Milky Way is larger still, but it's just one galaxy among trillions. And the universe, the vast cosmic web stretching across billions of light years, containing structures so large they challenge our understanding of physics itself, is beyond anything our ancestors could have imagined. And within that vastness sits the Hercules-Corona Borealis Great Wall, a thing that defies our expectations, a thing that pushes against the limits of what should be possible, a reminder that no matter how much we learn, the universe will always have more to teach us. The largest thing that exists is a mystery. And that's exactly as it should be. Thank you for joining me on this journey across the cosmos. If you found it valuable, please consider liking this video and subscribing to the channel. Your support helps me continue making these explorations of our vast and mysterious universe. The next time you look up at the night sky, remember the Hercules-Corona Borealis Great Wall. Remember that it's out there, stretching across 10 billion light years, containing billions of galaxies and countless stars, waiting for someone to explain why it exists. And remember that you, on this tiny planet, orbiting this average star, in this one galaxy among trillions, are one of the beings trying to figure it out. You're part of a species that can look up at the cosmos and understand, at least partially, what it's seeing. You're made of atoms that were forged in stars that died billions of years ago, and those atoms have organized themselves into a being capable of wondering about atoms in galaxies billions of light years away. That makes you part of something extraordinary. That makes this moment right now valuable beyond measure. Sleep well tonight, knowing that you live in a universe of wonders. A universe that still holds secrets. A universe where the largest thing that exists is a Mystery that shouldn't be possible. And yet there it is, waiting. Good night.